I have started.
Welcome, everyone. Okay, welcome to the Valentine's Day, February 14th edition of What's a Microcontroller with Python and the Microbit v2.0. This is day one of a 3-day workshop. We'll be attending for each and every day, hopefully. If you're not able to attend, we'll be posting recordings of each of the sessions to YouTube and emailing about 4 hours, typically after the day's session ends, so that you'll have a link to get caught up if you're unable to make it on any of the days. I'm going to first post you a link to this slideshow in the chat. Let's see. Now, am I sharing the wrong screen? It looks an awful lot like I was.
There's a slideshow.
Yeah. Okay, so let's repeat this. Welcome to the January 14th edition, Valentine's Day edition of the What's Microcontroller with Python and the Microbit v2.0 workshop. Day one, there will be 3 days. Each day is an hour-and-a-half session. And for any of you who are unable to make a particular session, you can get caught up by watching a YouTube recording that we typically post, usually around 4 hours after the end of the session. Here is a link to the slideshow I'm using. We'll have you use this to basically, for all the links that I'll be following, they are going to be in the slideshow. So, so it's an important resource to save for future use. All righty. Also, when we post it to YouTube, the link to this slideshow will also be under the Show More option on the, basically below the YouTube recording, the playback portion of it. My name is Lindsey. I've been working for Parallax for about 20 years, and my background is in electronics engineering by training, but for most of those 20 years, I've been developing educational materials for Parallax. And most recently, I have been focusing on the microbit. And so two of these, there have been two things I've been working on with the microbit. The first is the Cyberbot. I've been contributing to the collection of tutorials for that. And then also the What's a Microcontroller with MicroPython and the microbit. And so I posted links to some previous workshops, the online workbooks for both of them. So you could, for example, click online workbooks, follow the link, and this would be for the Cyberbot if you wanted to take a look at that. And then you can take a look at each page. Each of these links are basically chapters in a decent sized textbook of, in this case, for the Cyberbot. And then there's also equivalent links down here. So here, for example, is the textbook in progress for the What's a Microcontroller with the microbit. And then I also have earlier YouTube recordings of sessions for both the Cyberbot and the What's a Microcontroller. So why is this important? One part of that answer is that if computer programming education, computer science, electronics, regardless of what your entry point is, if you're just programming on a computer, there's a whole variety of computing devices that are programmable that the students might be missing out on. And in this case, that variety of devices all have microcontrollers like the Microbit microcontroller that we'll be programming today. And those microcontrollers are programmed once and then loaded into devices. And basically, if it has push buttons or a display, indicator lights, you can bet that inside it, there's a microcontroller that has been programmed and that might be reprogrammed during some kind of maintenance in some cases. Microcontrollers are also great for projects. Now, in some of these, like for example, in the Harbor Branch sub shown here, there's also several computer systems, but there are also microcontrollers in this case moving the lights around that are illuminating the seafloor. So microcontrollers are great for both inventing, and learning about them is good just for understanding another side of programming, which is how programs are made for the devices we use on a day-to-day basis. A little bit about Parallax. Parallax is a small business that has made a very large impact on both electronics and electronics education with some of their inventions, and then, of course, our curricula. This is Chip Gracie and Ken Gracie. They're the two brothers who, Chip is the chief inventor and Ken is our CEO. And they've been growing the business over the last, I think, 30 years, and education mainly in the last 20. Now, Chip's first and one of his greatest inventions is the basic stamp 2. And this was essentially the first microcontroller to make programming something like this and connecting a circuit to it and having it all work. It was the first device that actually made it approachable to younger students and hobbyists who were not necessarily ready to take a deep dive into the math that dominated electronics at the time in the mid-90s. Fast forward 20 years, and one of the new great educational tools is the Microbit Microcontroller. And it's really great. And since it's Valentine's Day, a few things that are great about it. First of all, it's got a built-in display, push buttons. It has a built-in compass. It has a built-in accelerometer for the step counting application here. It has a built-in radio so it can communicate with other microbits, and and then a light sensor. And if I didn't already say it, display and push buttons, and also a little strip of electrical connections that you can either connect alligator clips to or plug in it to an adapter and use on a breadboard. And all these features that are built into it make it just a great little microcosm for a cell phone. And it also has just outstanding educational support, not just what we have for it, but you can, for example, go into some of the just microbit-centric projects. And the first one I'm going to show you is, I'll paste this link in because we'll do this together. Okay, chat to everyone, paste. And there we go. So I'd like you all to follow this link and make sure it opens in your browser. And once you've got it open, look back at the Zoom presentation, because I'd like to show you a few things. We are focusing on Python today. And so this tutorial has some introduction videos, and then there's a graphical way of programming the microbit that you can use in makecode.microbit.org. But what we're going to be doing today is using Python. So under step 2, code it, make sure that you have clicked the Python link and that you can see some code that looks similar to what was in your homework. Okay, now the next thing that I would like you to do is click the Open in Python link here at the bottom. Or actually, you know what? In the interest of keeping this tab open for a second, go ahead and right-click it and select Open in New Tab. And then we can jump over there and we'll see the beating heart application, the beating heart Python script. And now we're basically ready to plug in our microbit to the computer. And once you've done it, what I'd like you to verify is that you were able to load the code and that it responds by showing you a beating heart. But more specifically, I'd like to make sure that all of our serial connections work. So the way I'd like you to do this after opening this is click this connect button right here. So when you click the connect button, you'll hopefully see a BBC Microbit CMIS-DAP choice that you can select and then click the connect button. Now, once it's connected, you'll get a little connection happy face in the picture, and then it'll give you the option to disconnect. So I am going to switch over to looking at everybody's faces here so that we can, oh, looking good, Elaine. Everybody else want to show me their beating heart, their heartbeat? Let's make sure we're all alive. Oh, cool. And Kristen has the battery pack connected as well. Looking good, Ari. All right, so we're good to go? Excellent. Now, at any point, please feel free to jump in and say, hey, Andy, could you hold up for a second? I still need to try to finish step X. And you're also welcome to unmute yourself and just jump in and ask a question. You know, especially since we only have, looks like 11 in attendance today. It's a small group, so we can definitely just kind of unmute ourselves whenever, talk freely. Make sure to remute yourself so background noise doesn't otherwise interrupt the flow of the meeting. Okay, so good. Quick question, are we all okay? So we all had some homework to do before the first workshop here. And so one of the things that we did was repeat things in a loop. And so we tried out those. And an important thing that I want everybody to remember is that if you have something like while true or for some variable name in range and some numbers, or if a condition is true, anything that's going to be followed by a colon here, that whatever is below and indented from that is what's part of the thing that will repeat either infinitely in this case or a certain number of times, or in the case of decision making, it'll be the thing that happens if the decision is true. And then if I put something below this, like print hello, this part is not indented. So if there was some statement in here that said, well, you know, if something happened, go ahead and jump out of this loop, it might make it here, but otherwise, in this case, it won't make it there. How are we doing on that? Does that make sense? And are we all feeling confident about that? Okay, excellente. Good, good. And another thing is I really want to emphasize how to save your work. So here I am. I have a modified, I'll put a comment here. We'll never get here. As written. Okay, so here I have this line 9 extra piece of code, and I want to save my work. So the way to do it, regardless of whether you're connected or not, if you're disconnected, you can just download a copy of your work. But if you're connected or not, doesn't matter, you can always save your work by clicking Load Save and then selecting Download Project Hex. Now, when I do that, it's pretty small and down in the corner, but do you see how beatingheart.hex appeared in my downloads? Okay, so now let's say that I want to make a change. So I'll go ahead and maybe delete this thing that the code never gets to anyway. And I want to save a copy of that work. Well, you can hit Load Save again and download Project Hex again, and you'll get another copy, but it's enumerated from the first one. And you can also do stuff like, so if we go back to the original code I had here, I can say that this is Beating Heart modified and save that. Now, here's the cool part. You can take these from your downloads and just drag them and drop them back into the editor. And notice that now that little, I just dragged and dropped the one that I saved where I deleted it. And then I can drag and drop the one where that I saved where I did have line 9. So this is an important thing because there isn't like a file save option like there is on, maybe Microsoft Word or other applications that you're familiar with. And so I just wanted to really emphasize, you change the script name and then download Project Hex, and then that's your and then that's your saved work. And in my case, need to open up Windows Explorer here. Where is Windows Explorer? Okay, I'm off on another screen right now. Just a second. Okay, so just to drive the point home, we're looking at my downloads folder on the left and a whole bunch of, all of my downloads history because I forgot to delete it. And you can also drag and drop your saved work from your downloads or any other folder that you decide to put these into your editor. Now, there are a few folks who might have difficulties doing that. And if you do, you can always hit the Load Save button. Pardon me for a second. Okay, you can always hit this Load Save button, and then or browse for a file is the other way to get to your saved work. So there we go. So remember that it's a really important point. And so I wanted to harp on it a little bit because of the fact that it's so different from some of the older applications that we might have experimented with. Let's try one more before moving on. Let's do my favorite is the step counter. So I'm going to open this up and paste you the link. Copy.
Can I just interrupt, Andy?
Yes, please.
Question, is there a save as in Microbit, or does it always enumerate?
The save as would be, so let me open step counter real quick. Or actually, no, I'll just go to python.microbit.org. That's the programming site that I was just at. Okay, so here we are in python.microbit.org, and we've got their default right now, Microbit program. So if I make a change in it, for example, I'll print hello to the terminal. All right, if I want to save that change, basically what you do is you change the name of the program. Granted, it will not overwrite the previous program, but the save as will allow you to say microbit program, modified. And then when you hit load save and download project hex, you will have a file in your downloads labeled microbit program modified. And so I'll go ahead and get rid of that change. And then now I drag microbit program modified in, and there it is. So essentially the answer is just change the script name and download another copy of it.
Okay, thanks.
Okay.
I have a question in the chat also. Mark is asking what the name of the app is that comes preloaded on the microbit.
Oh, the question, did you say, Stephanie, was what was the name of the app that comes preloaded on the microbit?
Mm-hmm.
You know what? I don't remember off the top of my, I do remember that I was able to find it on Google.
I just Googled and I thought you might know more. It says how to reset to factory default. So
there we are. That's the one.
I'll share that in the chat then.
Ah, thank you.
And apparently there's an Easter egg involving the buttons.
Yes,
sorry to distract.
Yeah. Hey, everybody, I have a better Easter egg. Let's do the step counter. Let's see. Did I remember to paste that in? Let's see here. Copy. And everyone paste. Okay, there we go. So this is the step counter. And again, the thing to do is to scroll down to step 2, and then right below step 2, the heading, you'll see options for make code in Python. Click Python, and then you'll see a button below the example code that says open in Python. And then once you've opened it, you can click connect, choose your microbit, and then flash. And in this case, okay, so here's the number 3 for 3 steps, and I'll shake it 4, 5, 6, and so on. And you can strap it to your shoe and it'll count your steps. So I'll wait for a little bit because I still see some beating hearts. Nice, looking good. Eduardo, Rebecca, Mark, Chris, there you go. Kristen's running. Ari, you need to get out there and take some walks. You've only got 0 steps. There we go. He took his massive first step. How are we doing, Elaine? Are you with us?
Yes, it lost its connection. I don't know if I opened it up a couple of times.
That may be. So you'd want to check the other tabs and see if one of them gives you the disconnect option.
When I click on connect, it's saying it sees it, but then it's not. It says no device selected. So I'm trying to paste it in one more time.
Oh, hey, let me show you something just to make sure that this isn't the cause. When you hit connect, oh, now it's not doing it for me. Let's see if I go over here. There we go. You got to make sure to select your microbit. So it's going to give you could conceivably have a bunch of different microbits connected. So it's important to make sure to select the microbit that's listed before you click connect.
It's saying up again, I have a couple things open. It's saying, let me try it one more time here. It's saying Python microbit wants to connect, no compatible device. I'm just going to unplug it here for a minute and plug it back in. See if that helps. There it is.
Well, that's good. At least unplugging and replugging will make that
Yeah.
whatever happened go away. Excellent. All right. So, and then while we are at the, while we're at this, notice that we have while true. And if the accelerometer dot was gesture, which means anytime since the last time it checked, if it did not detect a shake, it's going to skip everything that's below and indented from it. And so essentially, if you don't shake the microcontroller, all it does is repeatedly check and then, say, okay, well, I'm skipping what's below and indented between there, and there's nothing else left in the while true loop. So it's doing this. Okay, then when you do shake it, at some point, it'll go, oh, so it was shaken since the last time I checked. So let's go and add one to a variable named steps, which incidentally was initialized as 0, and then show that on the LED display. So does that make sense? Again, in the context of the tutorial, we did a little chapter, the very beginning of a chapter on if then, or on if statements. So is that okay as you're looking at the code? Make sense? Seem reasonable?
Mhm.
Okay, jump in with questions again, if anything does not make sense. All right, so these examples that I have in this slide right here are actually part of a larger set, a larger workshop that's a microbit only workshop. And I've got a link to the slides at the bottom and the 2 YouTube presentations. And Ed Mondragon of Granite School District graciously allowed us to share this workshop with everybody. He did it for his district, and it went pretty well. And especially day one is really interesting. There's so many neat things on the Microbit site. And with that said, we're going to move on to the What's a Microcontroller material. So today we're going to put together our electronic prototyping system that has the Microbit as its programmable brain, as well as its programmable test equipment. And then on Wednesday, we'll work with a few of the devices that you find inside common products, those being indicator lights, push buttons, and we're also going to connect a servo motor to it and do some position control stuff. On Friday, we'll do a few demos and experiment with a knob that you can twist called a potentiometer. And we'll focus more on curriculum. On Friday, we'll talk about the teacher resources. I'll try to reinforce some of the student resources that we have been using. And we might even have a guest speaker to talk about the standards alignment and teacher's guide that she's been doing, along with questions, exercises, and projects. So here is everything that was in your box when it arrived. And again,
Andy, we're not seeing your screen.
Oh goodness, I'm so sorry. That's right. That's one of my biggest Zoom habits that I really need to try to break. Thanks for letting me know. Okay, share screen, number 2, share. Oh boy, so you were not able to see this then? Oh geez. All right, so very quickly, this is the slide that has the YouTube links and the slideshow for the Microbit only materials that are at microbit.org. There's truly a wealth of material there. And so there's a lot of opportunities. If you go and watch this workshop, you'll see that there's a lot of opportunities for doing some programming, some additional programming only exercises before moving into something like electronics prototyping, which is what we're focusing on here. This is the list of what we're doing today, and I'll skip repeating it. Well, no, I'll just give the really quick summary. Today, we're going to get our system set up. Wednesday, we're going to experiment with a few devices and programming the microbit to control and monitor them. And we'll also take some electrical measurements on them. And then on Friday, we'll focus mostly on curriculum. But a couple demos. And then let's see. Now you can see this screen. You can see the parts now. Excellent. Thank you. So these are all the parts that came in the box. And so far you have probably managed to fish out the microbit and, or at least so far, all we've asked for is to have you fish out the microbit and programming cable and just make sure everything can communicate. Now, this is just a quick example of how you can actually do a pretty involved application circuit once you're not using just the microbit. Now, when you have the microbit alone, all you've got are 5 little pads that you typically use to connect alligator clips to. They're labeled 0, 1, 2, 3V, and GND here. And only 3 of those are really good for signals. The other 2 are just power connections. So when we, but by plugging it into an adapter that plugs in turn into a breadboard, now you can do all kinds of neat stuff. And be careful, I see an error here that I need to go and remove everywhere it occurs. I believe the red wire is supposed to be on the left. So this is kind of showing you how to plug in the battery pack backwards. So be careful about that. Red wire on the left, not the right, and not the right as it is in this picture. This is a slide where basically I talk about some of the ideas behind the kit. But in the interest of time, it's roughly 40 hours. And the standards that you're going to find at the high school level are going to be in CTE, specifically engineering, computer, or electrical pathways. Also, a quick blurb about jobs going down those pathways, especially with the national reshoring effort that's been going on. The jobs in tech are growing, and this is really important skills and knowledge that we're covering here for students, and something that has had kind of fallen out of the school curriculum over time, unfortunately. This is just for anybody who's watching along in YouTube later. This is the homework that was assigned and that we all did before this workshop started. So there's a link at the bottom to the actual homework assignment. And that homework assignment basically talks about following, gathering up materials, following certain links, and doing just a specific thing on that page, typically in the link that you follow. So it looks like a pretty long list, but it ends up not taking too long. There's also a walkthrough clip that is helpful for the sake of orientation. And so it's a little orientation video on that's basically in support of the homework and kind of like an extension of this workshop. And now to today's main topic of getting our stuff constructed and ready to do electronic prototyping with. This is learn.parallax.com. And you can just look along for now. This is the documentation site for Parallax Education. Now, if you change that learn up top to www, you end up at the Parallax store and support site. So this is where you would go to potentially buy microbits or cyberbots to sign up for workshops, to download software. And again, so that's www, and then we'll go back to learn. And this is where all our student and teacher resources live. The student and teacher resources for the What's a Microcontroller with Python and the microbit is right here. I will paste you a link in just a little bit. Currently, I just want you to look on and notice what's happening as I browse this learn.parallax.com site. So when we get to the main, textbook in quotation marks, it's an online textbook. And so there's the prereqs, which are just basically getting set up with your microbit and making sure that it can talk with your computer and that you're familiar with writing Python scripts. Then the main lessons here are tiles, and each one is essentially a chapter in a textbook. And we are pretty close to adding the next chapter, and you'll actually work out of it a little bit before Friday. Let's see here. So we already went through this as homework, all these prerequisites. And so we're ready to start breadboard and testing with the microbit. And where that is this is the link in the slideshow. I'm not ready to paste you a link yet. I'm still kind of showing where to go and what to do. So here is the overview page that you land in, and you can go through the contents by clicking along the left here, or you can also just click the next page and go through it like a book. And so this one I'll paste over to the chat. Paste, there we go. So what I wanted to show you on this page is that we have some animated GIFs for the students, and it makes the page not take up so much space. But if you are working with your students and you want to really talk about, in this case, a breadboard, you can open up the full size video clip. So this is kind of this animated GIF, you don't have really any control over playback. But when you open up the full size MP4, you can hit pause and play. And you can say, okay, well, this whole thing collectively is a breadboard. And then the breadboard has two parts in it. This particular breadboard has what are called terminal strips. And terminal strips are where the majority of the circuit building happens. Then we can go further and say, hey, look, there are some row numbers on the terminal strips. And they also have column letters. And that you can, I'm just kind of fast forwarding here, and that you can say, hey, go to socket G16. And so you find the column G and the row 16. And now you know that we're talking about a particular socket. And then the breadboard system that you have will also have bus strips. And those are typically where power, where the voltage that you want to connect to circuits is made available to any circuit on that breadboard. Okay, so that's an example of, here we have an animated GIF. And then in the student resources, we have a link to the MP4 version, which you can play and pause. It's not just important for lecturing, as you'll see in a second, it's also important for following instructions, or it makes it more convenient. So at this point, what I would like, yes? Oh, I thought I heard somebody.
Sorry, I just sneezed.
Oh, well, Gesundheit. Okay, so at this point, I would like everybody to gather the edge adapter and the breadboard out of the box that we sent you. And I'll stop share for just a second and make sure to, so here's the box. And typically the adapter is going to be right on top. And it says Edge IO adapter for the microbit. Then the breadboard should be way down at the bottom. And it will look like this. There we go. So those are the two additional items that I want you to grab. And I'll now put their pictures back up on the screen. Share screen. Numero dos. There we are. Okay, everybody got them? Excellente. All right, so now here is another animated GIF, and this is a point where instead of necessarily being a piece of lecture material, we have an MP4 so that in addition to these little checklist instructions that you see above and below the animated GIF, the students can actually open up the higher res pausable MP4 and see that, hey, step one is taking your microbit and inserting it into the microbit edge adapter. And we want it to sink in about that far so that you can just barely see that line of holes that's in the microbit edge. That's this part right here. And we're plugging the microbit edge into the microbit edge adapter. Looking good, Elaine. How's everybody else doing? Let's see some boards. All right. Okay, perfect. See, some of you have been working ahead. It's okay, bear with the rest of us. All right, so then we say, all right, take your breadboard and make sure that it's oriented so that you can see the A, B, C, and 1, 2, 3 in the top left. That's going to turn out to be important. And then down at the bottom left, you'll still see A, B, C, but you'll see, 27, 28, 29, 30 instead. Okay, once you've got it oriented that way and your edge adapter right next to it, go ahead and just set the edge adapter on top. Don't push it in yet, but see how the little pins in the edge adapter are going into A30, A29, etc., all the way up to, I believe, A11. Let me make sure that's right. So anyway, that row of pins needs to be started in those column A sockets with the P0 labeled pin on the adapter going into the A30 socket on the breadboard. Now, once you've got that lined up, and there should be a couple of pairs of pins that are sinking into this left bus strip, that little piece of vocabulary, the strip with the red and the blue stripes by them. Okay, and once you've got them lined up, okay, and again, we're emphasizing here where the pins should be, and we're actually zooming in just to make sure we've got everything perfectly lined up. And I know you guys are good with this, but especially students, it really helps to have these visual cues to really look a little closer, okay? And so once you're sure you've got all these connections started on your breadboard, what you're going to need to do is press down firmly. Okay, so those pins need to sink all the way in so that the little plastic headers that are underneath the piece of fiberglass that is the edge adapter is right up against the breadboard. So when you're done, it should look like that. See how just the little plastic pieces are the only parts that are visible, and the pins have sunk all the way into the breadboard? So, and you may need to use some pressure to do it. And then we've got, not sure which way is correct here. Okay, I think hopefully that's basically upside down. There we go. All right, looking good, everyone. So then we can move on to making some electrical connections. And this is the next activity in the chapter. Little thing here, in the interest of making it compatible with both Microbit 1.5 and Microbit 2.0, we took out the beep portion. And so all you'll see when you have two wires connected together, you'll see a little check mark here in the measurements. And then when they're not connected, you'll see a little, no sign. Let me, oh, that's right. Okay, so I'm getting ahead of myself. The MP4 for this is on another page. So first of all, let's talk briefly about terminal strips. I just want to show you that the way electrical connections work on a breadboard, in case you don't already know that. Some of you won't, some of you will. So all these little rows of 5 sockets are connected just as a row of 5 sockets electrically. So you can plug 2 things into a given row of 5 sockets and that will electrically connect them together, but they won't be connected to the row above or below. Okay, so as an example, if you pick a row of 5 sockets, you can plug 2 wires in there and they are electrically connected.
You're back at showing you full screen again.
Oh, thank you. Andy's habit of not Andy's habit of not going back into slideshow mode strikes again. Okay, so let's go back to, here are our terminal strips, and they have rows of 5 sockets. Okay, and on a terminal strip, you can pick a row of 5 sockets, plug 2 wires in there, and then those wires are electrically connected. If you were to connect some sort of power circuit, hopefully not just a power circuit like a battery, because that would be a problem. It would be a short circuit. But if you were to connect something to this, electricity, as in the flow of electrons, could go in one wire through the row of 5 and out the other wire. Now, so those 2 are connected because they're in the same row of 5. And this is another talking point for the students. If you pick a different row of 5, you put a wire in there. Well, since the 2 yellow wires are not in the same row of 5 sockets, they're not connected. But if you put another wire in that row of 5 sockets, those 2 wires are connected. Those 2 wires are not. Neither are those. And those are connected, but again, only to each other. So that is how the terminal strips work for connecting components to each other. Now there's a valley in between the 2 sets of rows of 5 on this terminal strip. And so if we connect to this row of 5 here, yeah, these guys are connected to each other, but because of the fact that it's not the same row of 5, those 2 wires are not connected. Neither are those. Those guys are not connected. But if you take a wire and connect one row of 5 to another, then you're connected. All right, so folks, is that helpful? Does that get across how connections on a breadboard work? Okay, good. And are there any questions before we move on? All righty. Again, just jump in if there are. All right, so we also have bus strips. Okay, so these are the bus strips, and they have a different set of rules for connection. Basically, if you have one bus strip, all of the sockets on the column are connected to each other. So if you have a column of sockets by the red line and you put 2 wires in there, they are connected to each other. No matter how high or low you go with those wires, if they're in this column, they are connected. Now there's a column next to it by a blue line, and that's a separate bus. And so even though those 2 are right next to each other, it's not a row of 5, you're in the columns, so they're not connected. Now, because of the fact that these are 2 completely separate columns here, they are also not connected. But you can add a jumper wire to connect the 2 columns, and now these 2 wires both in columns with blue lines. Since the jumper wire goes from one blue line to another, they are now connected. And that is the end of the breadboard intro. Again, jump in if you've got any questions. I'm going to skip this in the interest of time. And do I really want to do that? Yeah, I think we're going to come back. No, I think I'll end up regretting it. So let's go ahead and grab these parts right here. These are 3-pin headers. They're little 1/4 inch long, maybe 3/8 or close to a 1/2 inch long groups of 3 pins. Grab your red and your black alligator clip. 4 black or two black wires, 1 red wire, and an extra jumper wire, preferably either blue or yellow. Okay, and then I'll go through how to plug those in. Okay, so what we're going to do here is basically the 3-pin headers. Oh boy, I better let you guys get all your parts. So I'll grab my parts too. That way I can kind of get a feel for when you're all ready. Let's see here. There we go. So we're going to start with just 1 red and 1 black wire and 2 3-pin headers. And they should have come in a gray anti-static baggie, Ziploc baggie. All right, everybody good? Okay. So next up is you're going to plug the we're going to plug the 3-pin headers next to P0 and P2 with 1 socket open in between them ideally, but it doesn't actually matter for now. And then we're basically going to grip one end of the red wire with the red alligator clip and plug it into the 3-pin header that is plugged into next to P2, basically row 28, column CDE, and row 30, column CDE. That's where the 3-pin headers go. And then grab wires with the ends of your alligator clip, and then with the other ends of your alligator clip, go ahead and clip on to those 3-pin headers. And even though it's not necessarily showing that you really want the alligator clip to gobble up those 3-pin headers. So get as much alligator clip onto those headers and gripping those 3 pins as you can when you connect the alligator clips to the 3-pin headers. I'm hoping that the best way to pace myself is to do this along with you all. Important part also, when the alligator clips are grabbing the 3-pin headers, make sure they're not touching each other. There needs to be a small amount of airspace between any. Oh, I'm sorry, I missaid that. The plastic holders are fine touching each other, but we don't want any metal part of the alligator clips touching each other. Now, I probably should have said to disconnect your USB cable. I think in the instructions, it does say that. So have we all got something like this yet? Still working? 2 thumbs up. All right, let's give it some time, folks. Oh, let's see, there's some more.
Where can I find the reference for the pins numbers that I'm putting my wires in?
Okay,
Yeah,
so
can you pause it, please, on that?
yep, just a minute.
I can't see that, so I have bad eyes, and I just need the pin numbers.
Okay, so the pin numbers, if you take the pin numbers are P0 and P2. And then I had a request to pause it. I'm working on that. Okay, how's that look?
Were you
Excellent.
asking for the pin numbers for where to put the 3-pin headers or where to put the black and red wires?
The black and red wires.
Okay.
I found that you're on the Parallax Learn site, so I'm just trying to navigate to that page so that I can look at the details, right?
Okay, working on that. I'll go ahead and paste it in if Stephanie doesn't beat me to it.
Yeah, it's going to show me there, I think.
You're ahead of me
Thank
this
you.
time.
Let's see here. Except for I can't find the chat. Okay, there we go.
It's 16 and 17.
Mm-hmm.
Perfect. Thank you so much.
So what is 16 and 17?
The black
Oh, I
wires,
see that.
yeah, the black wires in row 17 and the red wires in row 16.
Ah, okay. So let me zoom into that. There we go. Does that help? Is that Kristen? Kristen, tell me if you can see that.
Yeah, that's good. And I have the Learn Parallax reference, so thank you. Yeah.
Okay, good, good. So one quiz you could give the students at this point is, hey, everybody, since I'm plugged into row 16 with the red wire and 17 with the black wire, are they electrically connected? And there might be some debate. And so the next thing we'll do is actually run a script that will tell us whether or not they're connected. Okay, are we all ready or do we still need some more time? Okay, give me a thumbs down if you're not ready. Okay.
Quick question, Andy.
Yeah.
How sensitive are these particular boards to electrostatic issues?
Surprisingly not sensitive. They are, so that the first session or the first training that I went to that an organization called cyber.org put on, they their presenter took a microbit and threw it at the wall and it bounced off the wall, and he went and picked it up and said, these things are not particularly, they're not the over delicate electronics that we're familiar with that needs an anti-static mat and all that stuff.
Okay,
So-
that answers my question. Thank you.
Okay, certainly. All right. So next up then, let me close my tabs for memory conservation on my computer. Okay, so next is to download Continuitytester.hex. So I'm going to chat you this page that we're on. It's the next page, actually. And the important thing to do with Continuitytester.hex is to right-click it and select Save Link As. And either put it in a place that you can always get to, or I just let it go to the default of downloads. So we want Continuity Tester. We want to download Continuitytester.hex. And again, that's right-click Continuitytester.hex after going to the site I chatted you. Select Save Link As. And then save it in downloads for hopefully easy location, or any folder that you pick. Just be ready to get to that folder in your file browser. Okay, and then the next step after that is to go to one of your editor instances, and I'd recommend closing some of the others if you have several open. So that's python.microbit.org. I'll paste that into copy, paste. Now, once you have Continuitytester.hex downloaded and your editor open, drag and drop the Continuitytester.hex that you downloaded from your downloads or from that little ribbon along the bottom of your Chrome browser into your python.microbit.org online editor. And if anybody's computer is being persnickety about that, you can always hit load save and then select or browse for file. And then look in your downloads and you can double click it and open it that way too. So we all got that open. Okay, good job, everybody. So next, if you're not connected, like I'm not connected, hit the connect button. If you're already connected and it just says disconnect, you don't need to worry. So Stephanie, are you there?
I'm here.
Okay, my computer screen just went blank, so I may be.
Do you need to switch over to your other computer?
I might, but I'm gonna keep going here for a little bit until. Oh, there we go. I think I just got it back.
Okay, because we can see you and your slideshow just fine.
Okay.
Right now we see the Microbit editor.
All right. Well, if I disappear, I'll probably just unmute myself on the other one. And
Okay.
all right, let's see. How are we doing for time? We've got 25 minutes.
Yes.
All right. So here is our continuity tester. Let's go ahead and flash it. And after you've loaded the code, we just want to try a couple of node tests here. So by node tests, what I mean is that we are going to first check and make sure that when we're in 16 and 17 with those two wires, that we're not connected, that we see that little no, like the no, It's the circle with a cross through it, no sign that you might see with no smoking or no jaywalking or whatever it is. And then if you're, what you don't want to see is a check mark that says you're connected. You want to see that no circle with a slash through it. And then once you've verified that you're in 16 and 17 with your wires and you see the no slash, try unplugging the black wire from 17 and then plug it into 16 and verify that you can see the check mark. Now it needs to sync well into 16. For some reason, I've got a wire with kind of a short end here. I'm going to need to check with our supplier about that because that's not something that we ever want to have happen. And so make sure that your wire sinks a good 1/4 inch into the socket. And once you've plugged both wires into 16, we want to verify that you can see a check mark on the Microbit's LED display. Okay, so I just finished switching the wires over and I have that nice check mark. And you can actually just unplug a wire to get back to the not connected sign. And then if you're interested in trying it, you can also probe the columns. So like I'm going to plug 2 wires into, see if I can have you see that. I have both wires plugged into the red column on the side. And now I'm connected. And if I unplug the black wire from the red column and plug it into the blue column, then we have not connected. See if I can. So there we are with 2 different columns and the not connected symbol. So that is our Microbit continuity tester.
If we comment out the line of code that plays music, should we hear anything?
If you uncomment the commented line that plays music, it depends. If you look at the underside of your Microbit.
Okay.
Okay, somebody remind me, Watchdog me to reshare. Okay. So thank you, Stephanie. Let's see here. I'm trying to unobscure the view I have of this.
It's a bit blurry. Are you trying to point out a microphone?
Yeah, no,
Are you
I'm,
at-
there we go. Are we any better now?
Sure. What are we looking for?
We are looking for, oh shoot, you can't even see it.
I'm 1.5.
Okay, so if you have a 1.5, you will not hear the sound.
Oh,
Thanks for having pre-identified your your Microbit version. Yeah, if you have 1.5, uncommenting the sound will not make any difference. And if you uncomment it, it will not be if you have a Microbit 2 point something and you uncomment this by removing the hashtag /# to the left of the this is the line we're talking about right here. So if you have a Microbit 2.0, you will hear 1/10 of a second long 3 kilohertz pitches indicating that you're connected. If you have a Microbit 1.5, uncommenting that will not do anything.
but does the Microbit 1.5, doesn't it play some sort of sound some way?
Oh, yes, yes. If you connect something called a piezo speaker to the breadboard, then,
Okay.
then you can send tones to it.
Okay. But the 1.5 doesn't have a built-in speaker.
Correct. Correct.
Okay,
Only
got it.
the 2.0 has a built-in mic, speaker, a little extra program memory / RAM. And what else? Mic, speaker, RAM. The next thing will come to me at some point. I'll remember the other features that the 2.0 has.
That's okay. I ended up with a classroom set, I think of 1.5s that I haven't used yet, and I wanted to bring it into my Computer Science 1 class this spring after the seniors leave.
Okay, perfect. Well, we are, this is fully supporting the 1.5.
Yeah, so this is going to be fun for my sophomores and my juniors in
Oh,
May.
yeah.
Yeah, because the seniors leave like the first week of May, so I've got 2 more weeks with them.
Oh, that'll be great.
Yeah.
Yeah, I think they really will enjoy it. Okay, so then, so we've tried probing the breadboard, and then there's always basically the way this is set up is that we have kind of the general information. In this case, we have a little bit of extended general information. We don't usually have 2 pages of intro. Then we have our parts in our circuit, script, the tests, which we just completed. Then for the students, we're going to skip this, but basically it's essentially trying a bunch of different connections, the same ones that were in the video clip I played earlier. Then there's usually a how it works. And then that how it works also at the end will often have a your turn, which challenges the student to do something, which is typically solved for the teacher, but not necessarily for the students. All right, so now let's go ahead and add some power to our circuits. You can go ahead and leave the 3-pin headers stuck in your board, and then just set aside the alligator clips for a minute. And let's see here. Whoopsie.
You want us to unpower our board before we start playing with circuits?
Yes, please. I always forget because there's never any consequences with the microbit. Thank you. Yeah, go ahead and disconnect your USB connector from the microbit or from your computer, whichever's easiest.
That
And-
microbit went in so hard and came out so easy.
So did you basically pull on the USB cable and the whole microbit came out?
Oh, yeah, I did. I mean,
Okay.
I'm trying to be a 15-year-old boy here, so.
Well, either way is fine. I mean, ideally unplug the cable, but if the whole microbit comes out, that works too.
I did not mean to pull the whole thing out.
Yeah, that's fine. Just make sure to plug it back in, display up.
Yeah.
Although you can actually plug it in the other way and it'll still work. We have it set up so that everything still works properly, but no blue smoke rising from the device. Anyway, so here are the wires that I want you to add. Is this zoomed in enough? Let's see if I think that's about maximum zoom.
It looks good on my computer, but I can't speak for all computers.
Okay.
Hey, Andy,
Yes.
I'm looking at the 3-volt pin.
Uh-huh.
Is that at the same number 11?
Okay.
Oh, wait, you know what it is? I'm sorry. Never
Yeah.
mind. Excuse me. I'm sorry.
So the 3V pin, you want to be on row 11 when you're connecting to the 3V pin. And then on the other end, you can pick any of the sockets in the vertical column next to the red line. I think I'm going to catch up with you all.
Excuse me, Andy.
Yes.
Thank you very much for your time. I have to log off a little early.
Okay, so again, we will have the YouTube video up. I'll be emailing you some homework.
Okay.
And it's just building a few extra circuits on the board for Wednesday.
Awesome. Thank you very
Okay.
much.
Have a good one.
Have a good day. Bye, everyone.
Eduardo, did I say that right?
Yes.
Good.
Bye.
Bye-bye.
Andy, are you gonna send everybody that homework? Because I might need to bow out when my husband gets home.
Yes, it's Valentine's Day.
Oh, no, we've been married too long for that. No, it's actually beautiful outside and I want to get 10 miles of bike riding in before the sun goes down.
Okay, well, yeah, yes, we've got the YouTube video. The YouTube video will appear about 4 hours after this. You know, I'm going to try to minimize that time. Maybe it'll only be 2.5 or 2 or something like that. It takes some time for Zoom to process, and then it takes
Right.
some more time for YouTube to process. So on the download and the upload, there's a waiting game. So yeah, we'll have that up as soon as possible, and then I'll send you out an email with the homework and and the link to the YouTube video.
Okay, that would be great because tomorrow morning is my off period and that's when I'm going to work on it.
Okay, sounds good. And then all of you remember, you can give me a ring or email and say, hey, Andy, can we meet over Zoom at, insert time here? And I'll do my best to accommodate you or suggest another time. For best results, send me time ranges, but I'm always happy to do some Zoom tech support, anything to help make sure you don't get stuck and are feeling good and confident by the next session.
I'm not going to do that. My off hours are 6 o'clock to 8 o'clock your time.
Oh, well, the 8 a.m. I can do that. I can do a 7 a.m. session. I just need warning the day before, I think.
Right. No, I'll be fine. Just
Okay.
watching. This is great.
All righty.
I am so doing this in May with my kids, if not sooner.
Oh, splendid. Well, and we've only just got started, so I hope it still looks good by the end. I'm thinking it'll look even better.
Yeah, I just need to go find money to get 15 edges.
Okay. Oh, just the edge adapters. Gotcha.
Right.
Okay. Let's see. How are we doing? Has everybody got that wired up? Okay, I still see some heads down. So, you okay, Rebecca? You're good? Okay, excellent. So let's then move on to connecting a light circuit. So, incidentally, I've got all kinds of close-ups here in the animation. Okay, so what we'll do next is we'll put the alligator clips back on, and this time I'm going to give you a link, and we're going to download and run Measurevolts, and then we're going to here. Actually, I better show you this one. So heads up, everyone. I'm going to show you the step-by-step. Oh, that's right. You guys all did the Cyberscope already, but let's just make sure. So, I'll copy and paste this in a second. So right-click Measurevolts, select Save Link As, and download. Just watch along right now. Okay, so then that's going to be at the bottom left of Chrome. And then we'll switch over to the Python editor, drag and drop it in. Now, you're probably all disconnected, so you'll need to plug your microbits back in, and then after doing that, you'll need to hit connect, and you may need to choose your microbit and select connect again. Okay, after you're connected, drag Measurevolts onto your python.microbit.org editor, and you'll see from multimeter import star. That way you'll know you've got the right one. Okay, so after you've done this, flash it. Click flash, the button flash, then click disconnect. Then we're going to have you go, and I'll paste all these links in just a minute. The next thing we're going to have you do is open another tab and go to cyberscope.parallax.com. In Cyberscope, you can click connect and find your embed serial port. I have some Bluetooth stuff going on here too. Got to ignore that. All right. And nothing happened. Okay, I should be seeing something. Let's see. Oh boy. Yeah, that's not a good sign. Connect, flash. Okay, disconnect. Actually, no, I'm going to stay connected for a second and I'm going to look at what messages are coming through here. Oh, that's right. Okay. I forgot that we are at the point where we are just going to look at it in the, well, since I got everybody started on this, let's just look at it in the Cyberscope. So there will be a line 8 that we're going to change from terminal to Cyberscope. Capitalization won't matter. Flash. Disconnect. Go to cyberscope.parallax.com. Click connect. Okay, and now you will see 3.29 volts, which means that you're plugged into one black or one blue column and one red column, one of the left 2 of those bus strips. And we'll go ahead and measure the voltages. All right, so where are we on time here? We've got 8 more minutes. Let's see here. All right, so I'll go ahead and paste you all these links. So first, this is the one where you're going to right click and download Measurevolts.hex. And I just lost my screen that has the chat on it. Let's see if I can make that come back. Chat. Okay, let's see if this will work.
Are you meaning to share your, there we go.
Okay, I got it. Paste. Okay, so that's the page where Measurevolts is. And then of course you're gonna open you're gonna download Measurevolts.hex, drag and drop it into Microbit editor, flash it, and then I'll paste you in cyberscope.parallax.com. And the other thing though is you want to change this to Cyberscope. So change terminal to Cyberscope before you hit flash. Capitalization does not matter. By the way, we're also open for questions and answers after the session. So the 1:30 end time is just the end of the official presentation, but there will be time for questions and answers after this. So I'd like everybody just to make sure that if their alligator clips are plugged into the supply rails here, okay, so when you're plugged into the supply rails, that one I don't want to worry about so much, but okay, here's a good spot to pause. So you want to put your red probe into the middle supply rails, red, the bus strips, column, any of the red stripe sockets, and then the black probe into the sockets by the blue line. And make sure that you see 3.3 volts there, roughly. And then also test over here to make sure you've got 3.3 volts. And again, you're going to be testing and seeing the results in the Cyberscope voltmeter.
Andy, can you go over how to connect the Cyberscope again?
Yes, yes.
I'm running on Brave and I just want to make sure that it's working as it should.
Okay, so step one is going to be, I'll refresh this. Okay, so this is where you should start, is cyberscope.parallax.com. Were you able to get there? Okay, so then there'll be a connect button here.
Huh?
So hit connect. Then you'll want to select something that starts with embed. Do you see embed serial port in your listing?
Okay. That's where it's not acting right. Let me hit refresh. Connect. It says, sorry, web serial is not supported on this device. Make sure you're running Chrome 78 or later. So I'll go move it over to the other browser.
Okay, yes, yeah. Yeah, this is a Chrome only thing right now.
Got it. That's why
Well,
I'm trying Brave just to see where it works and doesn't work.
Yeah, that's one of the things. I mean, we get a lot of hit and miss when we start moving features away from Chrome. So, sometimes it'll work on Safari and Macs, and sometimes it won't. Or there's various combinations of supported and not supported with the other browsers. Firefox is another one where some things work, but not everything. So Chrome is definitely your browser where it's all supported.
Okay. It's just I have way too many open tabs. My to-do list is on Chrome. So,
Oh,
okay. Okay, I'm there and I see 3.29 volts.
okay. Fantastic. So make sure to check a blue and a red socket in both the center and right columns, because we want to see 3 point something volts. And then if you put them in the same column, you want to see about 0 volts. And with that, you have a fully working system, and we'll start putting circuits on it. So that brings us to the homework for the next session, which is currently clear down on slide 43 through 5, but I might end up deleting some of these in between slides. Not sure yet. They're just screen caps of many of the pages that we visit. So this is what your circuit is going to look like on hopefully when you arrive to the workshop on Wednesday. A few little notes. The first is, this is the push button getting plugged into the breadboard. And it's important to verify that the little legs on the push button are sticking out the sides of the push button case, not out the top and bottom. So when you plug in your push button, it's going to be plugged in so that its legs straddle the valley in the middle of the breadboard on the right. And so here are the push buttons plugged into the breadboard. I'll send you a nice high-res version of this. The other thing is, if you're at all iffy about electrical or electronic connections, preferably everybody, especially remember that this is not right. These colors are backwards here. I might try to fix the colors. I'll let you know whether I did that in the picture I send you or not. You want to have the red on the left, not on the right, as it's shown here with the battery pack. Also, with this battery pack, leave the batteries out, because we want to do some testing before we connect battery power. And this servo connection that you see here is on another 3-pin header that's pushed into B3, 4, and 5. So this is something I'm going to go ahead and email you a more full write-up on it. And this is what we want you to plug in and have ready circuit-wise. One last thing, the longer pins of these little light-emitting diodes here, these are all lights. The longer pins need to be on the left side of this breadboard, on the left side of the valley on the breadboard where you see them. So towards the microbit edge adapter. And then the shorter pins will be on the right. I think that's all the main tips. I'll go ahead and reiterate that in the in the homework email. It is now 2:31. Thanks everybody for coming. You've been a really good group, and you're welcome to stay for, 15 minutes to 45 minutes, depending on how much there is to talk about. I mean, you're welcome to go at any time, but I'd like to keep you around, hopefully, to get some educator feedback so we can improve our program. But again, totally not required. Just questions, answers, open format. Stephanie, can you turn off the recording?
Stopping recording now.
Okay.